Okay. Hello, everyone. My name is Kevin Harms. I work at Argonne National Lab in the Leadership Computing Facility. So I'm going to be talking about some of our experiences working on DAOS. So this is just to give you an overview of how we're running or what we're running. So today our primary system is composed of 128 or 127 server nodes. So this is what users will normally use, and it's been running various combinations of 264, so within our C release and before that 263. Then we have a bunch of other nodes, and although we're not complete yet, we're trying to, hopefully this week some work will be ongoing to create a cluster that we'll refer to as DAOS Next that has like around 400 nodes. In the future, the goal is to take the remainder of those nodes and move them all over into DAOS User, and that will be the primary production system. And so I'm hoping by the end of the year that should be complete. So our primary production system will be 800 nodes. The remainder of the nodes will put the 200 nodes into the DAOS Next queue system, and that will be shared by Argonne and HPE. So we still work with HPE, and they do their own testing. So they use our compute system and run their own testing on, non-release versions. That still leaves some nodes left over, and so those will be hot spares or other various specific testing. We also have a small system Sunspot, which I'll reference some results from, and that's only usable by basically the internal staff. And so it's a 2-rack system versus the full size of Aurora. Okay, so very recently we've been working with one of the science teams that their code is called Hack, and it's a astrophysics or a cosmological code that simulates the universe. And so in the upper right here is data not from the run they just did, but it would look similar to this data. So there's a visualization, and this, our galaxy and star formations in these bright areas. So they were running on 8,100 compute nodes. So for our system, we have 6 GPUs per node, so you have 48,000 GPUs. And also, I forgot to mention, we have 8 NICs per node, so this is about 64,000 endpoints. They ran 6 days and then 12 hours a day. So they were normally running during business hours, so the various team could help support their run. And so they were using DAOS User for their output, and maybe checkpointing every 10 minutes or so. And so they were deleting old checkpoints as they went. One of the things we probably need to work with our users on is better estimation of their data storage resources required. But so throughout the run, they wrote about a total of 41 petabytes. But at the end of the run, they're only saving about 10 to 12 petabytes as their final results. And because we didn't have the GA release of 264, we were using a private build of a later version that had the defuse feature that lets you sort of do this collective mounting. So you use the local to global, global to local translation of the connection information. And so one of the previous problems we were having is mounting was taking a long time. And so this corrected the issue. And so we were able to mount within 1 to 2 minutes. We could even speed this up further by using like a more MPI startup, but at the time, our runtime below sort of MPI exec is PALs, and there's some issues sometimes when a process exit, even though you tried to demonize it, the PALs runtime is still tracking it, and so when you exit MPI exec, it'll kill everything that it knew was running. So to do the mounting, we use a Clush. And so Clush at 8,000 nodes takes some time. So now I'll go through some graphs, some sort of results. So the IO model that they use is a 2-stage output. So first, they write their output to /temp, and then asynchronously write from temp to DAOS. So as soon as the output to temp is complete, their simulation continues running, and they start draining their data in the background. So I'm going to step away here for a second. We have here, this is the performance here is in terabytes a second. So you can see on this bar was up to like 3.5 terabytes a second for write. and then this is read on the left. The intensity of the color sort of, I'm sure you can't read these numbers, but is the sort of the volume of data written. So this light color is 300 terabytes and this dark color is 360 terabytes. So for the checkpoints, the sizes are generally constant because they're based on the size of the volume that they're running. And you can see our read there's only maybe 10 reads that were done because you only needed to restart 10 times. So we're getting about 4.5 terabytes a second. And right, you can see is a bit more variable. So basically, you have a slightly smaller volume, but as you start running, things are great. And then their storage space gets full. And then at the end of some night, they're like, okay, let's delete a lot of things. And so then it's very fast. And then as it fills up, it slows down and they periodically empty out the space that they have to make room for new checkpoints. I should also say, like I said, this is average checkpointing. So because it's asynchronous, we take the start time and then whoever finishes last, we take that as the total time interval and divide that by the volume of data. So the instantaneous writes might be higher than these here, but.
Can you see the values from the application standpoint?
Correct. Correct. It's from the application standpoint, not from the measured from DAOS. So like I said, so the instantaneous rates could be higher at various intervals, but these are the average rates for checkpointing. So Hack also writes many other files more than represented by these three charts. So these are three types. These are analysis things. So these are accumulated during the run and kept. So I just put these in. They have the y-axis is different for all of them. These are for some different sizes. So here we have the peak to be 1.4 terabytes, and the colors are like small file, like are 1 terabytes in total aggregate volume, and then 5 terabytes is a darker, so single digit terabytes. And then in the upper right-hand corner is 10 to 40 terabytes. So you can see that's going up to 2.5 terabytes a second. And then the bottom graph has data below a terabyte to about, I think, 2 terabytes. So you can kind of see we have, and then the peak here is, I think, 0.8. Yeah. 800 gigabytes a second for the lower right. Yes.
Kevin, when you say Halo catalog, you're not referring to communication for Halo?
No, this is, Halos are, and this thing's like a Halo. That's about it. Don't ask me any more science questions. That was the limit of my cosmology right there. Okay, so we're very happy to get like generally good performance over the course of the time while we're running. And I think only 2 of these restarts, we had some issues with DAOS. All the other restarts are related to GPU faults during the run. So a significant improvement in stability over time. And again, this is all valuable data. So this is now like completely production system.
Kevin,
yeah.
Do you understand why checkpoints are so variable?
Like I said, it correlates to the fullness. So we allocate, I think they had a 10 petabyte partition of like, that's what we allocated because that's what they asked for. And they were like, oh, our analysis files are taking a lot more space than we thought. So they thought they could keep more checkpoints online, but basically you can see all these, there's a similar kind of spike pattern. This is just, these are ordered in the order that they were done in the run. But as the volume is full, it gets slower. So when the volume is empty, great, the performance is high. As it fills, it gets harder and harder to achieve the sustained performance. So, I mean, ideally, it would be better if they were more accurate with their size request. All right, so now I want to move to something else, which is unified namespace. So if you're not familiar with this feature, the idea is you can use a system like Lustre and then access using a special link your DAOS volume, and then your code can kind of translate to using DAOS, and then the user doesn't need to be as aware of how to set this up. And this is one of the things we wanted to do to make it easier. Like, users don't want to understand your storage system or how things work. They just want to be able to use it. And so we want to use this to make it easier. So This is still like something in prototyping, so the results here are on Sunspot. So I don't know if this will work, but I don't know if this is visible, but I'm on a login node, and then I'm showing the containers that are available. These are just ones I made. Now here, I'm just using a prototype, so I SSH to one compute node. And so I have the agent running. So normally always when you log in, the agent's running, and then Defuse is running under my permissions. So, and it's just pointed at this /DAOS. So if we, oh, I'm sorry. Let me. So we see here this symlink, the form mount is /DAOS, so those just match up. So you can't ls/DAOS, that's by design. It basically returns eno support. But if I eventually CD, so I have a few of these links created, you can see, and it enumerates how they're linked. So you've got the pool ID and the container ID. And then if I CD into this space, now this data is on DAOS, and I'm not using Lustre anymore. So I just have a few things in there. So we wanted to try to get this working. So that's the goal. So I've set this up, that just describes what I've done. And one thing is when you if your tools are kind of DAOS aware, so if you're using the intercept library, that we'll just start talking to DAOS directly. It will no longer talk to Lustre. One question I had, which I asked my Oak Ridge colleagues, and they gave me one answer, but in order for this to work, you need to be able to call setDirStripe. And our system does not allow the user to call setDirStripe, so this was not working. And so I had to ask the admin to go and change these parameters on the right there in the bottom right to say the UID to be -1, which lets anyone call setDirStripe. So I didn't know if we had any Lustre users or that know if their system allows the calling setDirStripe.
I think we can change just because we just want to set the foreign layout.
Yeah.
Right? We can just allow regular users to use the foreign layout and not change the directory stripe.
Yeah, so I think that's what, my Oak Ridge colleague says they also do not allow setDirStripe to be called. The reason why you don't let it be called is if you've set something up specifically and how your metadata distribution should be, you don't want the user to change it. So yes, one would be a new LL API, or just having the code say, hey, you're not trying to change the distribution, just setting the LMV, so that should be good. Any case, that's what I have. And I definitely want to say we would not be able to achieve the things without the help from our HPA colleagues. So Mohammed, who will be here later, Samir, Johan, John Kerry, and Sylvia, these people were critical in the success of our project. Any questions?